at IIT. So they come from there, and I saw them right after the master, and they became very incredible scientists, both of them. So I'm proud. I know she's embarrassed, but I'm proud to have you here. So Luna Gava is a postdoctoral researcher at the Italian Institute of Technology. She earned a degree in robotics engineering with honors at the University of Genova, Italy, and a PhD in computer science at the University of Manchester. She's currently working on low latency perception for robot interaction with complex dynamic environments. She supervises a project about a robotic air hockey player with event cameras and asynchronous Q learning. Other collaborative projects required eye tracking and human pose estimation with event-based cameras. A big round of applause, and thank you, Luna.
Okay, thanks, Julia, for the nice introduction. First of all, it was very emotional in the end. I didn't cry, I managed. And also thanks to the organizer because I'm really honored to have been selected as a iRising star. It was like a kind of an unexpected for me. So today I will focus my talk mostly on my PhD research work. The presentation title is Closing the Loop, Event Camera Challenges and Solution for Real-Time Tracking on Moving Robots. So already Julia presented a little bit me. Just to recap, I'm a postdoctoral researcher at the Italian Institute of Technology. I defended recently, last December, my PhD at the University of Manchester. And I have a master in robotics engineering and a bachelor in biomedical engineering. And my interests cover mostly computer vision and robotics. That's why I have always to join IROS like conferences for robotics, but also like CVPR, computer vision conferences. The Italian Institute of Technology, where I'm working, is based in Genova. That is this city in the north of Italy, 1.5 hours from Milan. Our group is called Event-Driven Perception for Robotics and is led by Chiara Bartolozzi. As you can see from the picture, we are like a 20-30 people group that is a multidisciplinary team. Not everybody's working on the same part, but we are all united by our mascot, the humanoid robot iCab. Maybe someone of you know iCab. We used to call our iCab in a different way to distinguish from all the other iCab we have at the Institute. And we used to call event-driven iCab because this robot naively has event-driven cameras in its eyes, but also because it's not only neuromorphic sensing, so we don't want only to emulate humans from the sensing perspective, so like trying to emulate the human retina for vision or trying to emulate mechanoreceptors for touch. We would like also to do neuromorphic computation in some way because we found that is promising to try to imitate, to try to develop algorithms that imitate how the brain works, because the brain seems to do very complex tasks at very low power consumption. Imagine that we know from scientific data that the human brain is consuming only 20 watt. That is like the consumption of a light bulb. So there is reason to have a look to humans to build better technology in robotics nowadays. To go on, I think you have seen many times this slide, especially on Monday workshop for those that were there, but even if you weren't there, in this community, I think everybody knows event-driven cameras. So today, I don't want you to reason on what an event camera is, on its advantages, but more on its benefits from another perspective. So to the idea of using event cameras for robots. So why event cameras are beneficial for robotics. So robots would benefit from event cameras, first of all, because since they have all these pixels in the sensor that are independent and asynchronous, they come up with a consequential property of low latency, high temporal resolution. Low latency means like the time taken to transmit a data, so from the change when it happens to the algorithm input is very low in the millisecond time resolution. It gives the possibility to robots to be more reactive. So if you reduce the perception time, you will have more time to act. That's really important for robotics because one of the main issue of robotics nowadays is the waiting time. So you just wait for a robot to do something, and we would like to delete this stuff and to also go towards more dynamic tasks is really important. Second of all, low power consumption. Of course, if the data is more compact, because it is the pixels are only sensitive to the brightness change, so only when something moves, it means you have a more compact data that is like this stream and asynchronous, like point cloud. It means you will consume also less, and so practically you could have lighter batteries on the robot, and the robot will be more autonomous consequently. Same for the computational resources. If you have like a lighter message to send in terms of events, instead of a full image, of course, you don't need any more GPU for sure, but even CPU, maybe you could use some neuromorphic platform, and you can even reduce also the computational resources. And finally, the high dynamic range allows the robot to be able to work in any kind of lighting or environment. You don't have to set up every time to tune the exposure time depending on the scene the robot is looking at. So, okay, this I think is something that you already know. But of course, there is a downside. All these advantages are good, but sometimes comes at a cost. So they bring some challenges. The fact that the output is sparse, as you can see, and asynchronous means it's a different kind of output to what standard computer vision is used to have a look to. And we need in some way to do a paradigm shift in the algorithm design, especially when even cameras are on robot, on moving platform. Have a look to the output of these cameras when the robot is moving just the head. You will see an increased number of data in output, but also a variable data rate is not always constant. Keeping that in mind, I found that in the literature, there was no available algorithm able to work, first of all, in real time, that is fundamental for robotics, but also in a very challenging condition. So having a moving camera, and you have seen the drawbacks of having a moving camera. A modern camera resolution, as Aaron was saying at the beginning, in the introduction, the fact that now the cameras are no more 128 by 128, but they came with the third or fourth generation, even higher, so you have more events coming in input, and also like the clutter from the background, because we don't want to have a constrained environment, like a clear background, but we want to deal with the real world. So these were the challenges in general, but from the algorithmic point of view, we have challenges due to the different kind of feature and different kind of data of frame cameras compared to event cameras. I want to reason you on that. So one issue is the fact that for frame-based cameras, you have these pictures at a constant frame rate, but the pixel inside the picture, so inside the shot, the camera is taking, have all the same timestamp. Whereas for event cameras, the events are timestamped. So every event has a different timestamp. So it is difficult to understand how to group these kind of events. But why do we need to group events? Because handling asynchronous events means handling events at irregular times. And a single event in its own doesn't mean anything. We need sometimes we need context. We need to know how is the scene to understand. So event representation are are ways to treat the event data in a way that is more manageable by downstream algorithms. And event representation are generated by grouping events in different ways. So you can see raw events that are this stream of asynchronous data. You actually start accumulating like a raw list of events over a constant time window, over a constant number of events, more naively. Or you can also do like smarter way to accumulate events, like these two kind of representation that I'm going to present later to you, Eros and Scarf, that as you can see, give like a constant, let's say a consistent object appearance across time. So always they have sharp and thin edges, facilitating the downstream task like object recognition. Why this representation, I call them smarter? Because they have this characteristic of velocity invariance. Velocity invariance, so I would like to explain you through this example. So maybe you may know, if you are in the community, this old data set of 6 degrees of freedom dynamic camera motion in Guillermo's lab, I think. So in this case, he was moving the camera, and he started, as you can see from the event rate, start to move the camera quicker and quicker. So the event rate increased, and as you can see, there are two differences between the two representations, scarf and temporal surface. You may notice that the scarf is always equally represented, whatever the event rate, whereas the temporal surface has some motion blur, so it cannot be used for downstream task algorithms in some cases, because we would like to have a clear and sharp edges. So velocity invariant representation like scarf or others like Eros and TOS are smart, not only because we developed, but also because they have this characteristic of giving velocity invariance, but not without a decay, not without a temporal decay, but the decay is given by the incoming events. So every time, and I'm gonna explain you through an example of Eros. So every time an event is coming in input, you put to the whitest value, so 255, and all the events in a nearby defined by K, by a kernel K, will be decayed. So imagine that an edge is moving from the left to the right. When it's moving, all the events that are generated on the right will decay all the events on the left, and will decay iteratively, subsequently. So this will in some way do ego motion segmentation, because you don't have anymore the motion bar. Is not the only challenge, the one of how to represent event. There is a second one, and the second one is the fact that if for frames, we always know how many pixels we send, how many pixels we process, because it can be computed by the width and height, so by the image resolution and the frame per second. For event cameras, we don't know how many events will be generated. Why? Because it depends a lot on the dynamics of the scene, on how the robot is moving, how the objects in the scene are moving. So it's a variable data rate, and consequently, it will be an unpredictable latency time taken to process. So what we thought was to think about how to ensure real time, whether, unless, even if the event rate was kind of increasing, because the event rate is increasing because we have these challenging conditions that are generating more events. So a naive way could be just take a region of interest and take a smaller resolution so that the event rate will decrease and we focus only on the object. But in this way, we lose all the context and the scene understanding. So no, it's not the best solution. We could use more powerful computational resources. So this will increase the CPU capacity. But in this way is not, let's say, a smart way to do that, because for robots, we want to keep the energy consumption and power consumption low. So the only way is to work on the first term, that is the time you take to process an event. So the time you take to process an event by the event rate gives you how much you take to do let's say the sensing. It is important to be feasible by the CPU. So how did we work on reducing this time per event? We were smart also in this because we decided to decouple the computation per event through an intermediate event-based representation creation, that it comes at very low time cost. So we do event by event update of this event-based representation, but then all the algorithm computation happens in parallel, asynchronously and as fast as possible on the latest available event-based representation. I give you also some results of what, to give you an idea of how much do we take per event. So these are different representations, and as you can see, the first column say numbers in the order of microseconds. That means you take something very small per event, but imagine that sometimes the robot moves so quickly that you get 10 million events per second. So that's a problem, an issue. Just if you would take the seats one, so 0.2, you multiply by 10 million, it gives you 2 seconds. So you are already off because it's no more real time. So we wanted to understand which one of these representation was the most, the best from the performance point of view. As you can see, SCARF, that I'm gonna present to the Spotlight talk, is able to handle 20 million events per second, ensuring real time. Of course, also the algorithm computation, so not the event, not the one event by event, but the one performed on the representation should be quick enough. And if it's quick enough, if we assume that it goes like at the 1-2 millisecond, the update rate of the algorithm, we start from the intuition that event cameras gives a continuous motion observation of the car. And if we take and we have a very high temporal resolution. So if we take two slices at like 1 millisecond, one from the other, we can assume that the car moved on independent, that we can predict that the car moved off only small amount of pixel, let's say 1 pixel, between two updates of the algorithm. So we predict ahead, taking a template of the car, simulating what could be the motion in these two slices, and we assume that the car could move on these independent axes. These are 6 degrees of freedom, plus the no motion itself that I didn't put here. So you can perturbate the object template on the left and the right to have some movement on X, up and down, and so on, roll, pitch, and yaw. And then our algorithm works iteratively by comparing the prediction that we make based on intuition that you have it's gonna move very small between algorithm updates because we have the event camera, and we compare it with the current state of the object. So we predict ahead based on the previous state. In the meanwhile, the object moved a little bit, so we assume how much it moved and we compared. And the one that is winning is gonna update the state, actually the components of the state corresponding to the winning. And this way we iterate and we find the object position. This is the output of our 6 degrees of freedom tracker. This is working in real time on a event camera. As you may see, on the left-hand side, you have the representation plus the template projected from the object pose. And on the bottom, you could see the high frequency rate in the order of 200 or 300 hertz. Okay, so they don't have many times, just to show you a practical example of how this works, how the pipeline works on a real robot. We attached an event camera to the manipulator, and as you can see, the robot was controlled based on the image features, and it was able to be reactive to the real object in a good way. Finally, we wanted to be sure that event cameras are responsive, not in general, but also compared to frame-based cameras. So we did a comparative experiment of frame-based camera and the event-based camera. The event-based camera was able to follow the fast tracking target, whereas the real sense not, because of the high latency the frame-based camera has. So I'm going to show you. What happens is that if you have the latency, there is a displacement of the object that is bigger. So the velocity control, so if you use like image-based control, the error will be higher. So the velocity control commanded to the robot will be higher. And so you have first instabilities, but then at a certain point, the robot just diverge, as you can see. Instead, event camera, having low latency, is able to follow and also follow changes of direction because it does just small and rapid adjustments that is more safe for the robot and is able to follow ahead. So to conclude, I show you like the robot responsiveness. I define the pipeline, able to handle asynchronous events and to be able to do everything in real time. But of course, there are still some limitations, and the limitations are for tracking high-speed objects. At the moment, I was moving the car not that fast. If the tracking doesn't recover from failure, so because if you have occlusion, for example, given from the hand covering the object, it can fail. And also the fact that you have to start from an initial known pose. So we would like in the future to improve the tracking accuracy, of course, to add maybe a detector to recover from failure and also to start the tracker, and finally explore the controller, maybe also consider an asynchronous version to be more reactive. Thanks for your attention.
Do we have any questions? Oh, wow. Okay, let's start from here.